Okay, so welcome to today's lecture. And as you might have noticed, Ole isn't here today. And also the usual person who will substitute Ole is also not here. And which is why I'm standing in front of you today. And this is my first lecture I've ever had, and I'm very happy about that because I think that's what I will do the rest of my life. So be patient, and if I talk too fast, please tell me so. And if I write too small, please tell me so. If you have questions, ask questions. So I would like to start with talking about the homework. And one of the things we often do in Mathematics 4 is to show that something is a vector space. And there's one definition of a vector space we have here in our book. And you have all seen this vector space definition. So let me just figure this out. So we have these 8 points here. And if we want to show that something is a vector space, technically what we can do is to prove and verify all of these 8 points. Okay? This is something we will usually not do, because this is it takes a lot of work to do this, and we have to remember all details, and that is something we usually will never do. What we instead will do is to use Lemma 127, which you can see here, which is a characterization of a subspace. So in today's homework, I just corrected, we were supposed to show that we had a subspace of some other space. And instead of verifying all 8 points, you should simply check, and we always do that. When we show something as a vector space in Mathematics 4, we always find a vector space V so that our space which we want to show as a space actually is actually satisfies this characterization. Okay? This is always easier than to prove all the 8 points. So whenever you are in Mathematics 4 and you need to show this, that something is a vector space, prove this by Lemma 127. Okay? Never go into details of showing all of these 8 points here. Okay? So that's one thing. And another thing is that in the homework, I often see that you guys write that, some things in Mathematics 4, they are just obvious. When you show something as a norm, and we have to show that the norm is greater or equal to 0, or that it's 0 if and only if the vector is 0, then we can almost see this just by the definition of it. And we never want to do that, actually, because when something is so simple, then you always have to show that the definition is satisfied. Okay, so you can't just say what you need to show. So when we show, for instance, that the norm here, just take my example, is greater or equal to 0 if and only if v is equal to the 0 vector, then you can't just say, yes, this is obvious. You can't just say, of course, the triangle inequality is satisfied. Because that's what you have to show. So whenever you have an exercise which seems simple, it's never enough just to write this, because you always have to verify and to give an example of why this is true. Okay? And some of you get mistakes because of that, because you simply you don't give reasoning why this is true, and you always have to do that. So never write in a homework that something is obvious. Okay. And another thing for our Danish students, that when something is bounded, in English, the Danish word would be begrænset, and not bundet. So an operator in Danish is begrænset, and not bundet. Just make sure to do that. How do I turn off for this? Okay. Great. Oh, Jesus Christ. Okay. Doing great so far. So what I want to do now is to relate some of the concepts we had previously in the lectures, okay? So we started out by having a normed vector space. And in normed vector spaces, we have several things. And one of the things is that we have addition and we have scalar multiplication. And next to this, we also have a norm, of course, which has to satisfy all the things a norm has to satisfy. After that was the first lecture. We considered normed vector spaces. In the second lecture, we considered Banach spaces. And Banach spaces are important because up here we have the problem that some Cauchy sequences don't converge to an element. And at Banach spaces, that is by definition of a Banach space always true. So here we also have a normed vector space where any Cauchy sequence is also a convergence sequence. And below Banach spaces, we also have Hilbert spaces. I'll turn on again. Okay. And Hilbert spaces, they are special Banach spaces because in a Hilbert space, we have an inner product. And this inner product is chosen in a very delicate manner. So not every Banach space is a Hilbert space because a Hilbert space is something with an inner product such that this here defines a norm, okay? Now, we have seen that every Hilbert space is a Banach space, and every Banach space is a normed vector space. But every normed vector space is not a Banach space, and every Banach space is not a Hilbert space. If this wasn't clear to you before, I hope this will be clear to you by now. And some examples of Hilbert spaces we saw last time was we had the classical space Rn and Cn, and then we had little L2 over the natural numbers. And spaces that are Banach spaces but not Hilbert spaces, we saw, for instance, LP on the natural numbers. Okay. And you see here we start with something and then we add more and more properties. You would also ask, well, can we also remove more properties so that we still have an interesting space? And you can do that, and that is not curriculum of this class, which is why I've written it in red. But there is the notion of a metric space and a topological space. Those of you who had Mathematics 3, they will know metric spaces and topological spaces. And we can continue the reasoning here. So every normed vector space is also a metric space, and every metric space is also a topological space, but not the other way around. So just be aware of that there's these more general spaces for those who are interested into that. The reason why we usually work in Hilbert spaces is because in engineering and in physics, we always work down here because when we solve partial differential equations or anything which has some kind of application, we usually look for functions which are in a Hilbert space. And now this turns back on, I guess. Okay. So what we actually want to talk about today is something completely different. So we start out where we left last time, which are operators on Hilbert spaces. And the operator we want to look at today is the adjoint operator. And those of you who take this class because of quantum mechanics, they will find this extremely important for you. Okay, so first, before we define the adjoint operator, we need some results from last time. So I'll just repeat that. So recall the following things. We have a functional, and that is a mapping, a linear map. Let's call it phi, which goes from a Hilbert space into the complex numbers. It only needs to be linear. Then we have, by definition of a boundedness, that a bounded functional is a functional such that there exists a constant let's call it k greater than 0, greater or equal than 0, such that the absolute value of phi evaluated and some vector v is less or equal than a constant times the norm of V. And this constant should hold for all V in our Hilbert space. This follows simply by definition of boundedness, where we have used here that the norm on the complex numbers is just the absolute value. Then there was a very important theorem that we had last time, and that is Theorem 443, which is also called the Rees representation theorem. And this is a very important theorem because it tells us that no matter which bounded functional we take, we can write this in the following way. So let's be precise. There exists a unique, let me call this U in the Hilbert space H, such that phi applied to the vector V is actually the same as the inner product between V and U. I know in the book that he has written W here, but I will call this U, so we don't confuse it with a W I will use later on. And again, this holds for all V in our Hilbert space. Okay. And what we want to do now is to consider the following. So, consider a bounded and linear operator, and we shall call that T, which goes from a Hilbert space into the same Hilbert space H again. In the book, we look at a bit more general setting, where we have an operator T which goes from a Hilbert space K into H. The reason why we look at this instead at the lecture is because this is exactly the same as this, but in the following we would just need to use notation, which is confusing. Okay, so the proof is exactly the same for this setting as for this, but it's easier to follow the proof here, and the ideas are exactly the same. So that's why we will do this here. Okay, so now we have an operator T. What else do we need? We need an element which we will call W in our Hilbert space H. Okay, and then we define the following. Then we consider the functional. We shall again call it phi of V, which is T applied to V in a product with W. Okay? And this you will show in an exercise today is bounded. So by exercise 416, phi is linear and bounded. Now, because it's linear and bounded, you can see we are exactly in the same setting as in the Rees representation theorem. We have a bounded linear functional. Therefore, instead of writing this, we can write the value like this. And that we do in the following way. So, because phi is linear and bounded, then because of, or due to Rees' theorem, there exists a vector in our Hilbert space H I leave a gap here on purpose because I'll write the name of that vector in a minute, such that, well, let's simply see what it says here. We have our phi on V, and we can write this well, it is defined as our linear bounded operator t applied to v inner product w. But by the Riesz representation theorem, we can write this as the inner product with v and then some other element here. Okay, whatever that element is, it is unique and it lies in our Hilbert space. So there's only one choice of vector which can lie here. Now, clearly it depends on w, and clearly it depends on t. So a good name for this is, well, since it depends on w, let's also write the w. Since it depends on t, let's write t. And since it's this special vector, which is unique, we put a star on it. Okay? So this now defines a map. How does it do that? Well, let's say this way. We have defined a map, let's call it T star, which takes an element, namely this here, of our Hilbert space and gives us another element back, namely this. Yeah, so let's say which maps W into T star W. Yeah, and in the book, if we consider the more general situation where we have an operator like this here, then it would mean T star goes from H into a Hilbert space K. This map here is what we call the adjoint operator. And we have defined it in such a way that exactly this equation here is satisfied. Okay, so we don't know how this vector looks like, but we know it exists because of Riesz representation theorem. This is a bounded and linear functional. Hence, we can write it like this. We simply call this vector, which over there is called u, T star W. And in that way, we've defined an operator T star, which takes our W here and gives us whatever back we need here. We know it's unique, hence this map is well defined. Okay? There's only one way we can make this happen here, this equality, by choosing the one element which is given by the Riesz representation theorem. When I had this class 3 years ago, then Ole said, I'm sure you understand nothing of what I've just done. And the reason he said that was because this is highly untrivial, because usually we say an operator is something which takes an element and gives something back, maybe v squared or something. But here, we don't know at all how T star works. We simply know it takes an element and gives us the one back we have here. And even though it's defined in this strange manner, we can say something about T star. So this is Theorem 451. So the mapping T star, which goes from H into H, is linear and bounded. And this is not clear at all why this should be the case. Because again, the only thing we know is that we have this equality here satisfied. In fact, the equation is called 413 in the book. Okay. So let's show this. Let's start with linearity, because linearity is always a bit simple. So what do we need to show? For a map or a function or a mapping, whatever you want to call it, is linear, we need the following. So T star applied to alpha times v plus beta times w needs to be equal to alpha T star v plus beta times T star w. And this needs to hold for all V and W and H, and for all alpha and beta in the complex number, because we are in a complex Hilbert space. So how do you show this? Well, what do we know? We know that let's call this U, and then we have C star alpha V plus beta W. This is the only thing we can start with, because this is the only thing we know our adjoint operator satisfies. We only know that this equation up here is satisfied. We don't know anything else. So this is the only place where we can start. So what is this equal to? Well, we can simply use the definition. So you see here, I have my T star on the right-hand side, and I can just put it on the left-hand side without the star. So then I have T applied to U has to be the same as alpha V plus beta W. And now I have no problems anymore, because now I have my linear and bounded operator T here, and I have a linear combination here. Well, we can simply apply rules from our inner product, saying that if we have a linear combination on the right entry, we can take this out, and the scalar factors here, they come out with a complex conjugation, right? So we get alpha complex conjugated, Tu, and V, plus beta complex conjugated, Tu, W. Well, this here again is a linear and bounded operator, hence I can put it on the right-hand side of my inner product, as I can do here. So this actually is the same as, keep my alpha outside, so alpha U T star V plus beta complex conjugated U T star W. And then again, I use my linearity of my inner product in the second entry, and then I get U alpha T star V plus beta T star W. Now this looks quite promising. However, we're not quite finished, because what we need is this. And now here we have, well, the inner product between our left-hand side here with a U is the same as U with the inner product of this element here. So can we now be sure that this actually is the same as this? We can, because this here holds for all V in our Hilbert space. And because of that, then this here also holds for all, let's say, U in our Hilbert space. And V and W, they are also just vectors. Now, we have not seen a result yet that tells us that this then has to be the same vector in the right entry. But there's a result, and this is called Lemma something, Lemma 442. And it is this here. So here you can see Lemma 442, uniqueness of vector associated with the functional. We have two inner products, V, U equal to V, W. And these has to be the same for all vectors V, just like they are the same here for all vectors U. Then whatever is on the right-hand side here is the same as this. So because of that, we're actually done. And we can write, yes, indeed, T star is a linear map, because we know that we can take the linear combination out of the operator. So we finish by saying, hence T star is linear. And this was by Lemma 442. Okay, so that was linearity. But the theorem says something else. It says that it's bounded as well. And boundedness is something which is always a bit tricky to show, especially here because, again, we only have this equality, which we know that T star satisfies. So, bounded. So what does it mean to be bounded? It means that we have to look at the norm of T applied to some vector V. But now we have a problem because we want to look at the norm by definition of boundedness. But the only thing we know of our that has to be T star. But the only thing we know of our operator T star is with inner products. So do you know anything which relates inner products with norms? We had something last week. So Theorem 414, and we've proven quite, well, I think almost all of them now. So do you see anything which tells us something about the norm with the information about the inner product? Yeah? The last one, exactly. So that says that if we want to know the norm of an element, then we can look at the supremum of the absolute value of these inner products. And this is nice because we have inner products here. So when we look at this, then this is the same as, apparently, the supremum of the absolute value of, and now what I want to do, you see, the V in the norm is in the left side of the inner product, but I want to have it in the right side. Is that a problem? Can I write W T star V? And then I take the supremum over all the W's with norm 1. Is this the same as, yeah, what do you say? Exactly, because I take the absolute value, so if I want to switch the entries around, I can do that if I do the complex conjugation, but the absolute value of a complex number and its complex conjugate are the same. So this actually is no problem at all. Okay, so what do we do now? Well, the only thing we can do, again, is using the definition of T star. So we can move this over to the other side, so we get TW V. And now we're happy again, because now we have something about T. And T we know is linear, and we know T is bounded. So what we can do now is we can use Cauchy-Schwarz. So let's say here, this is Cauchy-Schwarz. This up here was 4145. So, okay, by Cauchy-Schwarz, that's the uppermost equality here, or inequality. We know that whatever is in here is less than or equal to the norm of T, W times the norm of V. And because this number here is bigger or equal than this, then the supremum of all of them will also be bigger or equal to this. Okay, and now we use that T is bounded, so therefore we can do the following. We can say, well, this is at least also less or equal than the supremum of all W with norm 1, where we have the norm of T. We can take this out because this here is less than or equal to the norm of T times the norm of W. Okay, but we take the supremum of all W which have the length 1. So therefore this is exactly the same as norm of T times norm of V. And now we're happy because now we have that the norm of T star applied to any vector V is less than or equal to norm of T times norm of V. And this holds again for all vectors in our Hilbert space. And what we also get from this is that the norm of T star is less or equal than the norm of T. Yeah? From here to here, I use the boundedness of my operator t. If t is bounded, then I can because t is bounded, I know that t times w is less than or equal than norm of t times norm of w. Okay, and because this is greater or equal than this equality or inequality holds here. Okay. Okay. So now we know that if we have a linear and bounded operator t, and we define our adjoint operator like this, then our adjoint will also be linear and bounded. Yeah? Oh, yeah. So the supremum, that disappeared because we looked at all of these numbers here where the length of w, or the norm of w, was equal to 1. Hence, this will always be a 1, no matter which element we look at in this set here. So the only thing we're left with is norm of t times norm of v. Okay. Yeah. So, as I said, when we have a linear and bounded operator t, the adjoint will also be linear and bounded. This, of course, poses the question, so what if we now have t star? What happens if we take the adjoint of t star again? And so on. That question you will answer in the exercises today, so I will not talk about that. And what we want to do now is to do some calculations. Because the question is, how do we find t star in practice? So we know it exists, but we don't know how it looks like because it was only given by the Rees representation theorem. And this poses a question because the representation theorem doesn't tells us how this vector looks like. So can we still calculate it in practice? And the answer is yes, we can. So how do we do this? So let's take an operator which we know is linear and bounded. We had one last week, which is this one. So this operator is linear and bounded. It goes from LP into LP, hence also from L2 to L2. Right? We need a Hilbert space, so we can't just take P equal to something. So for P equal to 2, this is a linear and bounded operator, and hence it has an adjoint. And the adjoint, well, what we need to do is to satisfy this equation up here. So somehow there is an operator T star such that these inner products will be the same. So what we want to do is we take a sequence, let's call it xk, and I will drop these indices because we know what we talk about. In LP, L2, sorry. And then we look at the only thing we know that we have to look at when we want to find the adjoint, namely at T applied to xk inner product with yk. Now, and this is the inner product in L2. Right, so how does the inner product look in little L2? Well, it's the sum, infinite sum, over... let's not do it this fast. So let's first make a small step. So how should we do this? Yeah, I think I'll write it down here. So we have the inner product between, and then we have a vector here. And the vector there will be t applied to xk. So what is t applied to xk? Well, for x equal to 0, we get, x equal to, k equal to 1, we get the vector x1 plus x2, and then we have x2 plus x3, x3 plus x4, and I guess you see the pattern. Then inner product with y1, y2, y3, and so forth. And this inner product is the same as, and now, well, x1 plus x2 times, because this is the first component in this vector, multiplied by the first component in this one, complex conjugated, plus x2 plus x3 times y2 complex conjugated, plus, and so on. Let's just put the next one as well. So x3 plus x4, y3 complex conjugated, and so on. Now, a trick in mathematics is always to know where you want to end up. Because, I mean, this could be anything, but we know where we want to end up because we know that whatever we want to end up with is the inner product between our sequence, in our case here, xk alone on the left-hand side of the inner product, and then something, whatever it may be, on the right-hand side of the entry. And this right-hand side will be t star applied to our vector y. So where do we end up? Well, we have to do some calculations in between. I will not write those yet, but we know whatever we want to do, we have to end up with x1 times something, plus x2 times something, plus x3 times something. Well, x1 stands alone here, so let's try to isolate x1 here. So where does x1 appear? We have x1 only here, where it's multiplied by y1. Not here, and not anywhere else. So we have this. Plus, then we have x2, and x2 is multiplied by y1 complex conjugated. x2 is also here, multiplied by y2 complex conjugated. And x2 is not here and not further on either. And then we have x3, and x3 appears here. So we have y2 complex conjugated plus y3 complex conjugated, and so on. Aha. This is quite nice, because now we actually know. Yeah? That is, of course, not correct. Thank you. Aha. Okay, so now we know how our t star looks like, because t star is whatever we have here on the right-hand side. And yeah, I don't want to wipe that away. Do we still need the proof of the linearity? I don't think so. So, just to finish this exercise here, we have, then we can see this is the same. So equality means whatever I've written last there. It's the same as inner product between, and then we have here x1, x2, x3, and so forth. This vector inner product with, now we just read off, well, y1, you know, recall that the complex conjugation disappears because we take the inner product. So y1, and then we have y1 plus y2, y2 plus y3, and so on. Now we're done, because now we know, okay, this here must be t star applied to our sequence yk, and it is given by y1, y1 plus y2, y2 plus y3, and so on. Okay, so now we know how we can calculate the adjoint operator, and this will always be done like this. No matter which exercise we have, and we have to calculate the adjoint operator, always you have to begin with the inner product, and then try to isolate your vector on the left-hand side, so that it's the only thing left standing on the left-hand side, and then whatever you have written under the complex conjugation, like here, that will be your adjoint operator acting on what we here call yk. And we don't even need to calculate that this here is linear and bounded, because we already know that. Linearity was written here on the blackboard, I just wiped away, and I also wiped the theorem away, but we also know it's bounded. So that follows just automatically. So that's quite nice. So this actually shows that our fancy definition up here, where we had said that, okay, there exists a vector here, t star w, so that this equality is satisfied. It's actually quite trivial when you have understood this, that the only thing we actually do is we say, okay, t is linear and bounded, we can just move it to the other side and use this as we would use t as a linear and bounded operator. We can move around with it as we used to, and we can just move it back if we want to as well. Note here that the operator can go from the left entry to the right entry by putting a star. You cannot go from the right entry to the left entry and put a star. You can go from the right entry to the left entry by removing a star, if you want to. Okay? Because it's just what we said here. So keep that in mind when you do the exercises today. And do I want to say something else about the adjoint? No. Okay, so today in the exercise you will also show something else about the adjoint operator, which was something I already mentioned before. And one of the results is the following. So this is Lema 452. And it says the following, and you will have to prove this. It says that the adjoint operator of an adjoint is actually T itself. Okay. And it also says that the norm of T is actually the same as the norm of the adjoint operator. We already saw here that the norm of T star is less than or equal to the norm of T, so the only thing we have to show is to show the other inequality, because then we get equality. And yeah, there's a hint. No, there's no hint. You have to be tricky here to prove this. And this here, it follows by using the fact that you can remove T and put T to the other side if you put a star or remove a star. That is a funny exercise. Okay. So I've talked for 42 minutes now, and I've come through half of my notes. So I think we should have a break now for 12 minutes, and we meet again 5 to 2. Okay.